Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI talk. My name is Frank Marchis. I'm a senior planetary astronomer at the SETI Institute and the chief science officer at Unistera. So welcome to the talk. Today we are going to talk about water, and more importantly, the importance of water and where this is coming from. Just a few logistics here. So this is a monthly science talk. We discuss recent finding in the field of astrobiology. You can tell us in the chat where you are watching us from. We have speakers from the UK at the moment, but I'm sure there is viewers from everywhere in the world. So please let us know where you are and watching us from. Sometimes even the city and the state, we will mention it at the end of this talk. So today's talk is about water. Water is a very simple molecule, H2O, but it's also a very precious molecule on Earth, because we believe it's a molecule which has been necessary to create life, to help for the creation of life. Water is everywhere in our solar system. We found water on satellite of Jupiter, the moon of Saturn, on Mars, etc. We know that water is everywhere. We even see water on exoplanets now. As I mentioned, because of this connection with the apparition of life, the search for water and the origin of water is extremely important for the field of astrobiology, so for the SETI Institute. So today we are going to discuss a mystery. Where this water is coming from? Is it a remnant from the Earth's formation? Was it brought to us by asteroid, meteor, comets? Or is it the result of some complex interaction with solar wind? And to answer to these questions, we invited two experts in this field, Daly and Ashley King, who have published numerous papers on an attempt to answer to this question. But I will let my colleagues, Beth Johnson, communication specialist at the SETI Institute, to introduce them and maybe to tell us more about the topic. Beth, it's all yours.
Thank you, Frank. Welcome again, everybody. I'm Beth Johnson. I'm a communications specialist here at the SETI Institute, and I am your moderator for today. Joining me today is Luke Daly. He's a lecturer in planetary geosciences at the University of Glasgow and a treasurer of the UK Fireball Alliance. He looks at the very small to get at the very big by tearing extraterrestrial rocks apart one atom at a time to try and understand what the solar system's environment was like before there were planets, how asteroids form and evolve, and how habitable worlds are made. Also joining me today is Ashley King. Ashley is a research fellow at the Natural History Museum of London, where he investigates the origin of the solar system and the formation of planets through the laboratory analysis of meteorites and samples returned by space missions. Ashley is also a member of the sample analysis team for the Hayabusa 2 and OSIRIS-REx missions and is the current lead of the UK Fireball Alliance, which is a collaboration between Meteor camera networks. Y'all should be familiar with that from our CAMS network here, and that aims to recover freshly fallen meteorites in the UK. So welcome, Luke, and welcome, Ashley. Thank you for joining me today.
Brilliant. Thanks for having us.
So as Frank was talking about, water is necessary for life on Earth, but we are still trying to understand its origin here on our planet. We have multiple hypotheses and papers coming out just last week. In fact, the most common theory right now is that Earth's water comes from meteors that deposited here when Earth was very young. And then over the eons, icy asteroids and comets have delivered what amounts to oceans here on Earth, depositing the water directly to the surface. But there are other scenarios. One suggests that most of Earth's water was already inside the planet and rose to the surface over time. And another says that the origin may be even more complex and could have been brought to us by the solar wind, for instance. So thank you again, Luke and Ashley. And what we're going to do is we're going to start with a couple presentations from the two of you. And Luke, I understand you are going to go first, and you're going to talk to us about water and how it got to Earth.
Yeah. So I'll just quickly share my screen. Let me know if you can all see that.
Looks good.
Yeah?
Yeah, looks good from here.
Perfect. Right, I'll crack on then. So yeah, thanks so much for having us. It's really great to be here to talk about where Earth's oceans come from. And In trying to answer this, we came across this potentially quite unusual idea that of a new reservoir of water in our solar system that might have contributed, or as I like to think about it, half a glass of sunshine. So I'd like to start with, the Earth is a really cool place, if you haven't noticed. It's the only planet in our solar system with liquid water stable at its surface, and also the only planet in our solar system that has life on it, so far as we know. In our local neighborhood, Venus is a vision of hell. It rains sulfuric acid and melts lead. It has almost no water in its atmosphere. Mars is really small. It lost most of its atmosphere and all its oceans, if it had any, boiled off. It's bone dry and cold at its surface. So one of the key questions we have in planetary science right now is, how does that happen? How do planets get their water? And the reason we don't think they started with much water, at least, is something called the snow line. Now, the snow line is in the early solar system when there's just a swirling disk of gas and dust. The sun, turns out, is really hot. And so inside of this plane in our solar system, water will be in the vapor phase because of that hot young sun. And in the outer solar system, water will be in the ice phase. Sorry, in the ice phase. And that young energetic sun, its solar wind will blow out that water vapor into the outer solar system and we lose it. And so the poor young Earth, as it's forming, won't be this lovely pale blue dot. It will be this relatively dry world. And so we then have this conundrum of, okay, where else could our water have come from? And the way we track that is by measuring the hydrogen in our water. Specifically, we measure the ratio between hydrogen and deuterium. Deuterium is just hydrogen, walks and talks like hydrogen. It just has one neutron more in its atomic structure, so it's one heavier. And that brings me to the problem graph of Earth's water. So Earth's deuterium-hydrogen ratio is moderately heavy. However, when we go out into our solar system and measure all the water-rich things, they are very different. So water-rich asteroids, on average, are slightly heavier than the Earth's ocean composition. Achondrite, stony asteroids, they have much less water, but also it is also slightly heavier. Comets are a real problem. They're really heavy in their water. We can add almost no cometary material to the Earth. Otherwise, our deuterium-hydrogen ratio would be all over the place. The reason this is a problem graph is you can't add three heavy things to get a light thing. That just doesn't work. And the only object on the other side of the graph with appreciable hydrogen is the sun. Now, I'm not going to suggest we throw the sun at the Earth because that would be bad for everybody involved, but we have this mass balance problem. We need something on the light side of this graph to balance the heavy books. And the solution might come from an unexpected place, and that's space weathering. Now, space weathering is a combination of processes from the sun's solar wind, which is a stream of hydrogen ions, micrometeorite impacts, and galactic cosmic rays. That affects every object exposed to the vacuum of space, be that comets, be that Mercury, be that the moon, or a billionaire's car, apparently, asteroids and tiny dust particles, and particularly the sun's solar wind, which is a stream of protons or hydrogen ions. You add those to rocks and they generate water by basically those hydrogen ions coming in and nicking an oxygen out of the crystal structure, producing OH and H2O. However, how much water we generate by this process has been unknown. And so we wanted to measure that. And so I was fortunate enough to get 3 particles from the asteroid Itokawa, brought back by JAXA's Hayabusa mission. These are all about the size of a human hair. So another unaccounted for source of Earth's water is the sweat from my brow and the anxiety involved with picking up a grain that's that small. But what we were hoping to see is these rocks that we've put in space, their outer surface should become slightly damp from the solar wind. So the outer few hundred nanometers should become enriched in water. And we needed to use a very special tool to measure this because it's such a small feature. And we used a machine called an atom probe, which literally tears material apart one atom at a time and reconstructs it in 3D. And what we saw is this beautiful enrichment in OH and H2O in the outer surface of our Itokawa grains. And so this shows that this sun solar wind is producing water in the outer surface of particles on the surfaces of asteroids to the tune of about 20 liters per meter cubed, which is a sizable amount. And while that's really cool, what's even cooler is when we think about even smaller grains like we had in the early solar system. Tiny grains, less than a few microns, could hold a substantial amount of water, up to about 1 atomic percent. And when we kind of think about what is falling out of the sky as us all the time, of the 50,000 tons per year that hit the Earth every day, meteorites, not very much, very small percentage of the relative amount of material. Asteroids and comets, They're very rare, but they add a lot of mass when they do come in. But by far and away, the biggest contributor by mass right now is tiny dust particles of that size order that should be irradiated by the sun and have a lot of water. That should be true right now. It should also be true in the past when Earth was forming. These tiny dust particles should be raining in along with water-rich asteroids. So potentially we could have a solution for this light isotope reservoir of small dust particles being irradiated by the sun, solar wind. We add them to the Earth alongside water-rich asteroids. And when we model this, approximately a 50-50 ratio of water-rich asteroids versus tiny dust particles could come together to explain Earth's water budget. Or as I like to think about it, half a glass of water in every glass, half a glass of sunshine in every glass of water. It's a bit of extra motivation to get those 3 liters a day that the doctor prescribed. Thanks very much for listening. I'd like to leave you with this cool thought about if you're standing on the Earth as it's accreting, you will see these whopping great water-rich asteroids raining down at the sky, out of the sky at you, as well as this beautiful shooting star display, which is literally raining water at you. And as implications for life in our solar system and life elsewhere in our galaxy, these mechanisms shouldn't be unique to the Earth. Every planet in our galaxy should get water in this way. So water might not be the rate limiting step for life. Thanks very much, and I'll happy to take questions in the Q&A.
All right, thank you, Luke. Ashley, you have a few slides to present as well to talk about some other ways, a little bit more detailed on a few ways on we get water here. So why don't you go ahead and take over?
I'm feeling like I should have included more rappers and wrestlers in my slides now. So that was brilliant, Luke. That was a really great introduction to why the solar wind, or what role the solar wind played in bringing water to the Earth. I'm gonna talk, I guess, about a more classical idea for where we think the Earth got its water from, and that's the role of these water-rich asteroids that Luke mentioned. And we always think of the Earth as this really incredibly wet planet. This is a photo I took many years ago on a sunny day in Chicago. We know that the Earth's surface is covered by, or 70% of the Earth's surface is covered by water. But really, actually, by mass, there's less than 1% of the mass of the Earth is water. It's actually much less than 0.5% of the mass of the Earth. So some of that is that surface water, but there's also a whole reservoir of water, which is actually very difficult for us to quantify in the mantle, so below the surface on the Earth. And yeah, as Luke said, one of the big questions we have in planetary science is explaining where that water came from, because we think the Earth probably accreted in the inner solar system, and therefore the temperatures were high, and we really didn't have many volatile species and things like hydrogen, or not so much, or not, at least not water vapor in the disk from which the materials the Earth accreted from. So I'm gonna just move this out of the way quickly. So one of the ideas is that's been hanging around for a long time is that the Earth accreted its water from a source elsewhere in the solar system. So that water was delivered by bodies that formed in water-rich parts of our solar system. So to get water-rich bodies, we need to have ices in the disk for those bodies to accrete. And so you're looking at the outer part of our solar system. And this idea of what we call the late veneer came about due to some kind of chemical studies that people have been able to do by looking at the composition of the rocks we have here on the Earth and the composition of the rocks, or the composition of the meteorites that we can study. And so the idea is if you go back in time to 4.5 billion years ago, the Earth's forming, it's probably kind of like a magma ocean type body, and you have differentiation taking place. Your heavy elements settled to make the core. And the core is iron rich. So what we call siderophile elements, or iron loving elements, should all be accreting and going into the core of the Earth. But what we find when we look at the mantle is that there's lots of siderophile elements within that mantle, and they shouldn't be there. And the only way we think we can get them there is by having this additional kind of extra sort of percent of material added to the Earth as part of this late veneer. So this is useful for explaining these highly siderophile elements, but it also gives us a mechanism for delivering potentially materials that are water rich to the early Earth. So one of the ways we think we can do that is through something called the Grand Tack that came about as a kind of partly to explain exoplanet observations a few years ago. But it also helps us explain what's going on in our solar system. And so just to kind of broadly, most of our meteorites come from these asteroids. These are small rocky objects out there in the solar system. We split them broadly into S-type asteroids, so stony asteroids that formed in the inner solar system. So these formed under higher temperatures where there wasn't really any water in the disk, and so they're dry. And then in the outer solar system, beyond the orbit of kind of Jupiter and Saturn, we have the C-type or the carbonaceous asteroids. And this is where we think bodies were accreting ices and we had water locked up in those asteroids. And so what the Grand Tack does is actually a mechanism for planetary migration. So Jupiter and Saturn actually migrate within the disk in the early solar system. And Jupiter and Saturn are so massive that they actually scatter some of those rocky S-type asteroids outwards. And then as they migrate back out, they scatter some of those water-rich asteroids from the outer solar system inwards. So this gives us a mechanism to kind of throw water-rich materials at the early Earth in the form of these asteroids and explain that late veneer. So what we do, and we both work on this, is to, if we want to understand what the composition or understand where the sources of water are coming from on the Earth, we need to understand its composition. We know the composition of the water on the Earth really, really well. And what we're looking for are chemical reservoirs out there in the solar system that have a similar composition. And Luke showed a really nice graph explaining this. And the way we do that is by studying meteorites that naturally arrive here on Earth, and also through sample return missions. So sending spacecraft out into the solar system to collect materials from these water-rich asteroids. And we had asteroid Ryugu came back in the end of 2021. This is a carbonaceous asteroid. And in September this year, we'll have samples from OSIRIS-REx. So that's NASA's mission to asteroid Bennu. And these are brilliant because these are pristine materials. We know exactly which asteroid they came from, and they're never exposed to the terrestrial environment, which is really important when we're interested in trying to study water. Everything on the Earth gets contaminated, so we want pristine materials. We can also do that to some extent through meteorites. And the example I put here is the Winchcombe meteorite. So this is a carbonaceous, so it comes from a water-rich asteroid. It came through our atmosphere and it was collected. The first material was collected about 12 hours after landing. So other than it landing on my lap in the Natural History Museum, we can't really get these materials any quicker. And that allows us to study that rock before there's been any significant terrestrial contamination and try and understand the water that's locked up within it. So Winchcombe, this is just, so you mentioned the UK Fireball Alliance at the start. So we have a network of cameras here in the UK that we use to track the fireballs. So this is what happens when the rock comes in through the atmosphere. And that allows us to work out where that rock lands. So we can go out there and collect it really quickly, like we could for Winchcombe. And it also allows us to start working out whereabouts in the solar system that rock came from. And so Winchcombe, we know that rock was knocked off a carbonaceous, a water-rich asteroid out there somewhere near Jupiter. So it's telling us about the sources of these water-rich materials to the Earth. So yeah, Luke showed a really nice cartoon of this plot. Mine's slightly more complicated. The idea is that we're looking for a chemical reservoir that has the same composition of the Earth's oceans. So the Earth plots here in this blue line. Luke said this is where the sun is. It has light. This is the deuterium to hydrogen ratio. So the sun is light. Most of our comets, which is what people often think of as a way of bringing water to the Earth because they have lots of ice, are actually really heavy. And then most of our meteorites are also slightly heavier than the Earth. We don't have a great match for any extraterrestrial material for the composition of the Earth's water. But what we could do with meteorites like Winchcombe and a few other similar meteorites that were collected really quickly is measure that water in them really, really fast. And it turns out they're not a perfect match, but they're not too dissimilar to the composition of the water here on the Earth. So that's telling us that these water-rich asteroids are playing a really important role in delivering water to the early Earth. There are lots of questions about when that water arrives, and we can talk about that a little bit more. And there's some chemical things that they don't quite explain. But the composition of water in these water-rich asteroids is a pretty good match for what we have here on the Earth. And I think I have one more, but I think I'll leave it there and we can chat.
All right. Thank you, Ashley. And thank you again, Luke. Okay, so there's a lot to unpack in this particular topic, simply because not only do you have multiple theories, but you're trying to understand how a fairly dry rock ended up with how much water does the Earth have in total, approximately?
So I think it's about 10 to the 24 kilos, I think is the rough estimate. It's a difficult then, and so it's less than 0.5% of the total mass of the Earth. It's a really tiny fraction of the Earth's mass. So we think of ourselves as being this really wet planet, and we're in the UK where it's raining right now, but actually the Earth is very dry.
Now, I understand. I'm in California, where it's been atmospheric river after atmospheric river for the last few months. So I think it's actually sunny at the moment. So that is a lot of water, even though it's a little bit of water compared to the rest of the planet. Luke, how does the snow line affect this? You kind of talked a little bit about, you know, the fact that there was some sort of gas in the inner solar system and then ice in the outer, but what does this leave Earth with?
Yeah, so I guess sort of summarizing the snow line is this idea that when we have basically no planets, we've just got a disk of gas and dust, that young energetic sun is going to warm up the gas that's close to it. And so water would be in the vapor phase. And the reason that's a little bit of a problem is it's not, Earth should be forming in that region, and that energetic sun should cause that water vapor to be lost to the outer solar system. But even while the water vapor's there, we need to if we want to have water being imbibed into the Earth at that stage, we need some mechanism to get that water that's very hot in the vapor into a rock. And there are some ideas about how one might be able to do that by absorbing water onto the surface of those grains. But it's really hard. Like when you've got something that's at incredibly high temperatures, it wants to boil off, not go into a rock. When we do that in the lab to figure out the water, we basically burn our rocks to thousands of degrees to make them exsolve all their water. It's a really effective way of losing it. So you can't really get sufficient water into your rocks in the inner solar system to produce, well, what we think to produce the amount of water that we have before it's lost to the outer solar system. Did I answer the question?
Mm-hmm.
I was just going to
go ahead, Ashley. No.
I think one of the questions we have is that we don't really know where the snow line was 4.5 billion years ago in our solar system. We have a good idea that, so I think today it sits somewhere in the main asteroid belt between Mars and Jupiter. But that doesn't mean that's where it was when all these rocks, when the Earth was forming and when these rocks. And I think what we've learned from the astronomers, and me and Luke are both kind of geologists who study rocks in the lab, but planetary science is a really broad thing that kind of covers lots of different areas. And so I think the astronomy, things like JWST, was starting to see where snow lines are in protoplanetary disks, and you can see they even migrate over time. So that's a big question I think we have, is to try and work out where that was when the Earth was forming.
Well, and Ashley, you mentioned in your slides that there is some discussion of Jupiter and Saturn shifting during the formation as well. So it not only does it seem like the snow line could have moved, but that our planets weren't where they were to begin with, and so that has had an impact on how this all formed as well.
Yeah. So this is I was going to say new. It's still relatively new for us idea, and this comes from exoplanet observations. Actually, when they first started doing those, they would see really big exoplanets that were really close to their central star, and that doesn't really make much sense because they are big gas balls. So all that gas shouldn't be similar to the Earth not having any water. There shouldn't be that much gas there to make something like Jupiter right next to the central star. So people started coming up with these models about how you can make these giant planets migrate within that protoplanetary disk. And then your snow line can migrate, and you can kick materials in and you can kick materials out. And so the early solar system wasn't this sort of static environment that we kind of think about it. It was really, really chaotic. There was a lot going on. So Luke, you both talk a lot about the deuterium hydrogen ratio.
Why is this so important? How has this become sort of the baseline for what you're looking at?
Yeah, really good question. I guess on its very simple terms, your deuterium hydrogen ratio changes kind of depending on where your object is forming in the solar system. And that's partially due to the sun destroys very effectively deuterium during the sort of nuclear fusion processes. And you generate deuterium really effectively in a molecular cloud through, again, atomic interactions that I don't pretend to understand with neutrons, etc., producing deuterium in molecular clouds that then come together to form a solar system. So you have a generation mechanism and a destruction mechanism. So if you're accreting more stuff from like closer to the sun or the sun solar nebula, which will be predominantly hydrogen rather than deuterium, you'll have a more hydrogen-rich water signature. Whereas if you're further out, have a more kind of
molecular cloud dominated deuterium rich signature, accreting more of that material into your body, you'll have a heavier deuterium hydrogen ratio. So the stuff in the very outer reaches of our solar system, the comets, etc., they have a ridiculously high deuterium hydrogen ratio. So we're basically using that mixture of those two reservoirs from the solar nebula, the sun, and molecular cloud to kind of fingerprint the water reservoir.
One of the really interesting things, though, is that what we call the ordinary chondrite meteorites, so these are the ones that come from the S-type asteroids, those rocky kind of bodies that we think formed in the inner solar system. So they should have more hydrogen than deuterium, but they don't. They actually have the highest D to H ratio of all of our meteorites. So, which doesn't make any sense. And there might be some processing on the parent body that explains that, but again, it's a thing that we don't really understand why that is.
So one more thing that leads to just more questions.
Yes, yeah, yes. It keeps us in a job.
There you go. So Ashley, you were talking about the different kinds of asteroids and the meteorites that they create or bring to Earth. When you talk about them bringing water to Earth, what sort of amounts are we talking about? We've already established that it's not a lot of water, relatively speaking, but it's a lot of water to get from smaller rocks. So how heavy was this bombardment? How many, obviously our water levels aren't magically going up every year as we get more asteroids, more meteorites. So yeah. What led to what kind of mechanism were we looking at for the time period?
So most kind of small asteroids are on the order of diameters of a few kilometers, tens of kilometers, and smaller. And so these kind of carbonaceous asteroids of that size, what we know from the meteorites from studying them, is that their mineralogy is mainly what we call phyllosilicate and clay-like minerals. So they're a little bit like mud that we have here on the Earth. And so these are minerals that formed when there was interaction between water and dust and rocks were on the parent body. And those clay and phyllosilicate minerals can hold about 13 weight% water. So these bodies are very, and those minerals make up about 70–80% of the whole rock. So they're really, really water rich. So you can get all the Earth's water from one pretty small, fairly average asteroid just hitting the early Earth. Doesn't mean so it's possible, it's likely there were multiple asteroids or multiple bodies that were hitting, but you can actually deliver everything in one go, potentially. And the challenge is when you bring that water, if you bring it too early to the Earth was hot. And like Luke was saying, is that hot things want to lose their water, basically. And if you bring it too late, there are lots of kind of chemical signatures that we can't quite explain as well.
Yeah, I'll just add to that as well. Like, we kind of think about how it might change over time. The reason we're not suddenly drowning is in that early turbulent period of the solar system, that's when we're getting a lot more impacts, a lot more collisions. So you're talking maybe we get 50,000 tons today, which sounds like loads, but it really doesn't change the mass of the Earth that much. Like in this kind of late Veneer, you're talking about 1% of the mass of the Earth arriving in a relatively short time period. Yeah. So kind of waterfall, kind of like you have over there with these big rivers of water falling out the sky at you.
So the late Veneer is estimated at about 1% of the Earth's mass. But actually, I think you need about 4 or 5% of what we call a CM chondrite or CI. These are the most water-rich meteorites to explain the Earth's water budget, I think, roughly. So those numbers don't quite match up. So the late Veneer is maybe not the best. It's maybe not when the water came. The water may have been delivered by these bodies earlier than that late Veneer, possibly.
Well, one of the things that you talked about, Luke, is the solar wind. So how does that come in? Does that fit into this? Is this a part of this entire mechanism, or is this a separate idea?
It basically starts to help us with the light isotope reservoir. And this whole idea came apart completely by chance almost. We were measuring this material we'd got from the asteroid at Ithaca, really cool stuff, measuring the space weathered surface to see what we saw. And we saw this whopping great enrichment of water. And that got us thinking, oh, that's a lot, like 1% in the outer 100 nanometers, a sizable chunk. And what about tiny grains? They'll be almost like 1% water in their entirety from this process. And sort of like looking at, again, using colleagues as astronomers, looking out into other solar systems, they're incredibly dusty places. So these regions, once the gas disk is gone, all those dust particles are going to be seeing that sun-solar wind, receiving water forming inside them as those hydrogen ions just stream in. And so the idea was, okay, let's for fun do a mass balance equation. How much of this could we add to the Earth during that kind of late stage accretion to balance that book? So the idea is not superseding the water-rich asteroid idea. It's just saying we need this lighter reservoir of water. We could potentially get it from tiny dust particles that have seen the sun-solar wind, because like we mentioned, the sun is destroying all this deuterium. It's just hydrogen coming in. So that deuterium-hydrogen ratio should be solar. So that's a very, very light isotope reservoir. And we only need 50% dust, plus whatever dust it happens to be, plus water-rich asteroids to get our deuterium-hydrogen ratio and water abundance.
And we're talking a lot about hydrogen because that's kind of like we use that hydrogen composition as our sort of smoking gun, finding what it was. But actually, there's there were lots of other volatile elements like carbon, nitrogen, and also the noble gases. We have to explain all of those as well as the hydrogen composition. And so meteorites do quite a nice job for carbon and nitrogen. But the noble gases, you need a solar wind component to be added in there. So this idea of having some hydrogen come from the solar wind as well fits quite nicely with that.
Yeah. I mean, like as I presented the problem graph for deuterium hydrogen, you basically have the problem graph for nitrogen, carbon, oxygen, up to and including ruthenium, which is really heavy, highly siderophile element. And you have the same graph. Carbonaceous chondrites, comets sit on the other side of the graph and the sun sits on the opposite side. I don't think the solar wind explains ruthenium, though.
No, I guess the interesting thing about the solar wind is that I imagine you would, if solar wind was implanting all that water, then all these bodies should be really water rich, maybe.
It's a good point. Yeah. But, to the tune of yeah.
I mean, we only have the samples we have available at the moment.
Yeah.
So the sample return, we've done that for 3 asteroids now, pretty much. The meteorites are wonderful, but they're just a random collection of rocks that come to us. We don't have samples of everything that's out there in the solar system. So it's possible there's one magical type of asteroid or rock that's out there in the solar system that explains everything that we just haven't found yet.
So Luke, how can we apply this research to other bodies in our solar system then?
So I guess what it suggests in some ways is that no matter where we're getting our water from, all these mechanisms shouldn't be unique to the Earth. The grand tax should destabilize all the small bodies. That should turn the inner solar system into a pinball machine of all these water-rich objects coming through. Dust should be raining out on every single one of those objects, no matter where they are. So Earth shouldn't have been the only planet that got water. Venus should have got water. And there's growing evidence that maybe Venus earlier in its history, sort of like beyond 4 billion years ago, was probably another blue planet in our solar system. And there's substantial evidence of oceans, rivers, lakes on Mars beyond 3.7 billion years ago. So Mars had substantial surface oceans. So there could have been 3 blue planets in our solar system. And so potentially when we're talking about origin of water, water should be common. Water should be everywhere. And what a planet does with its water after it gets it is its own business. And it depends on how close it is to its sun, how small it is, how big it is, to keep that nice habitable environment, to give life an opportunity to emerge from it.
Yeah, you pointed out in your slide that Mercury is a tiny little dry ball. Venus has this very thick, non-water-based cloud cover, and Mars once had water but is dry now, at least at the surface. We keep finding more and more evidence of bits of water everywhere. How does that? What would you want to do to find out how this all worked?
That's a phenomenal question. I think maybe me and Ashley might have the same thing. Go sample more things. Like, let's go out into our solar system, because we have very few measurements of comets. Let's go sample a comet, bring that back. Get some more measurements. Let's go see all these other water-rich asteroids, or see asteroids that don't match any reflectance spectra of any meteorite we have in our records. See, like Ashley said, if there's these potentially samples that we don't have in our meteorite collection that might be the oh yeah, suddenly all the pieces of the puzzle fall out and make sense. So yeah, just going out, sampling more things, making more measurements, collecting more data. Because I've got a hunch that while we're all throwing out the different ideas, different models, different sources, the grand tack makes the inner solar system a complete mess. So we should get something from everywhere. So probably the answer is going to be a mixture, not any one smoking gun.
So
Yeah.
Ashley, tell us about a little bit more about the Winchcombe meteorite, because one of the things you guys keep talking about is that you are managing to get some things from Earth that you can use.
Mm-hmm.
When was the Winchcombe meteorite? When did you guys acquire that?
So Winchcombe, the fireball was just before 10 p.m. on Sunday, the 28th of February, 2021. It's burnt into my brain. And as I said, we have this network of cameras that actually record the skies. And strangely for us, it was incredibly clear in the UK that evening. And so, and it was a very strange time because it was the middle of lockdown here in the UK. So we actually weren't allowed out of our houses pretty much to do anything. So we saw this on the Sunday evening. We saw the fireball. Our cameras picked it up. We were pretty confident that something had come down. We couldn't say exactly, what type of meteorite it was going to be. And then we managed to get the word out there, and we were really lucky that a family found it as basically a splat of material on their driveway the following morning, and they'd seen us on the news going, well, if you find it, take some pictures, put some gloves on, seal it up in bags, and let us know. And they just did all of those things perfectly. And as I said, it was about 12 hours after it landed. So really, as quick as you're going to ever collect one of those. And that's really important. We did the first measurements on that sample within days. We had the hydrogen and water composition measured really, really quick. So all meteorites are contaminated. They're coming through the atmosphere, so everything gets modified. But if you can collect them that quickly, you can kind of rule out, we can track. So there were two things. We know the contamination is very low because we got it very quickly. But also, because I work at the Natural History Museum and we curate meteorites. What's really important is knowing, we know exactly when that sample landed. We know how it was collected. We know how it's been stored, and we can monitor how things change over time. And this is really important for understanding what's kind of the extraterrestrial signature, what's the terrestrial kind of contamination on these rocks. So Winchcombe's, we have about 500, 600 meteorites that are very similar to Winchcombe and probably come from very similar water-rich asteroids. But for most of those, whenever you measure their composition of that D to H ratio, there's always, most of them are finds, things that were just collected many years after landing. And so they're all contaminated. For Winchcombe, that's probably pretty much as good as we're going to get short of sample return for understanding what the composition of those meteorites is. And it's not a perfect match for the Earth's oceans, but it's pretty close. It's pretty close.
So is there an ideal time frame for collecting a meteorite sample to keep it from getting very contaminated?
As soon as it possibly can. I mean, ideally, you'd pluck it out of the sky before it even came down and hit the surface. That's what sample return is. You go to an asteroid and you collect it and you bring it back and you keep it all locked up in whatever environment. But yeah, you want it as quickly. So we have about 70,000 meteorites in the worldwide meteorite collection. Most of those are what we call finds. So they're things that weren't seen to land and were collected just I'd say by chance, not quite by chance, but they were just found afterwards. When we go and get them from hot deserts, and cold deserts are particularly good because they're very, very dry and things can sit there relatively not contaminated. But really you want a fresh fall. And to do that, you need some luck, like we had for Winchcombe. But these camera networks, and Luke can talk about these, they're popping up all over the world. And they're absolutely crucial for us being able to work out where the rocks landed. Doesn't always mean we find it. We got really lucky with Winchcombe that it hit a driveway. But it also gives us the orbit. So we can start working out whereabouts in the solar system it came from, because most of our meteorites are just random rocks. They're brilliant. And you can study them, and we can, Luke can pull them apart atom by atom, and it's absolutely amazing. But if I'm a geologist, you just give me a random rock, I can tell you loads of stuff about it. But unless I know whereabouts it came from, you kind of lose all that context. And so that's what we want for meteorites, is a kind of, we want a geological map of the solar system. We want to understand what those chemical reservoirs are, partly to understand where the water came from on Earth.
I guess just adding into that, the reason we're concerned with these water-rich asteroids getting contaminated really quickly is, as Ashley said, they're mostly made out of clay. Clay, notoriously, well, very water-rich, notoriously rubbish at holding onto its water. It very rapidly exchanges with the atmosphere. So if it had a unique deuterium hydrogen signal, it would change very quickly to equilibrate with the Earth. So one of the questions is, are CMs all like the Earth because they've been contaminated, or were they like the Earth because they were like that in space? And Winchcombe is great because it, like 12 hours, you'd hope not a lot would happen in that time.
And the Ryugu samples that came back just before Winchcombe actually are a really nice example. So that's a carbonaceous asteroid, and those samples look a lot like what we call CI chondrites. These are the most clay-rich, most water-rich meteorites, and they're really, really rare. And those rocks you can see white crusts forming on those CI chondrites, and that's because they're basically act like a sponge. Those clay minerals suck up all the moisture, and it reacts with the minerals, and they just get contaminated within hours. And we could show that for Winchcombe as well. Within hours, they're contaminated. So the Ryugu samples are really, really similar to those, but they're missing some minerals, and some of their chemistry is a bit different because they haven't seen the terrestrial environment. And hopefully when Bennu comes back, we don't know what we're gonna get yet for Bennu, but hopefully something very, very pristine and fresh that we know hasn't been contaminated.
So by that token, what is Bennu sort of is OSIRIS-REx the biggest thing that you're excited about right now? Are there any other upcoming missions that have the two of you excited?
Yeah, I mean, yes, I'm very excited by it. OSIRIS-REx is kind of starting to slowly take over my life, very slowly. And so it comes back at the end of September. That's going to be very exciting. There's going to be a lot. So for Ryugu, they brought back just over 5 grams of material, which when you can study it atom by atom, that's plenty. That will keep us busy for a long, long time. For Bennu, again, it's a carbonaceous. We're expecting water-rich materials in there. And we're hoping for maybe 200-300 grams of sample. That's a lot of material for us to play with. So that's the next sample return. And then MMX is the sample is going to go to Phobos. This is a Japanese mission and Phobos is the Martian moon, but it looks a lot like a carbonaceous asteroid. So I'm very excited to see what Phobos is made of. So that's a bit later down the line. So I think that launches next year and comes back 2029, I think. These are very long missions, take a long time to get the money and then to launch them, and then you have to wait for them to go out there and come back. So we're very patient.
Yeah. Now, I'm super jealous of Ashley. He's going to get samples as part of the initial analysis team from Bennu. I'll probably have to wait a little bit longer to get my hands on some of that, but very much looking forward to that. I'll also add one last mission, which is still it's still yet to be fully greenlit, but there's a real strong plan to do Mars sample return and bring back the samples that the Perseverance rover is diligently drilling out of the Martian subsurface, and kind of going back to Earth being a data point of one. If we get those samples back from Mars, understand Martian water, what went together to make Mars's ancient oceans, or what's it look like now, that will give us a second major data point of the terrestrial planets in the solar system, and meant to potentially help us uncover origin of Earth's oceans and origin of water in the solar system. That's 2030.
Is there any interest in sampling sort of some of those subsurface oceans? Would that be of interest? If you could design like the dream mission, would you want to, go sample and say Enceladus or Europa, or, there's so many now. You have lots of options.
Yes,
all of the above.
All of it. I mean, I think the one I would, I'm torn. The thing I would really love is comet sample return that Luke mentioned earlier, because we don't really. So we I think we both sort of showed those plot where the comets have hydrogen isotopic compositions that are much higher than we see in the Earth's oceans. And that kind of makes sense because they probably got this ice that formed in the molecular cloud in these cold environments. But pretty much all of those measurements, all of those measurements are remote sensing. They were done by spacecraft that flew by near the comet. And they're not measuring the physical bulk sample, the ice and the rock. They're measuring the coma and the tail and the stuff that's coming off. And that can easily cause fractionation between that hydrogen and that deuterium that we don't really understand quite yet, I don't think. So it would be brilliant to grab, and there are plans to do this, to grab the ice off the comet and bring it back as ice and keep it like that and study it. And And that would be amazing. And that's who knows when that will actually happen. I'm sure it will happen. And then the question we'll have is, well, what we know from asteroids is they're all pretty different to each other. So, if just one comet, what does that tell you? You want to go and sample all the different types of comets that are out there. So that's one thing. The other dream for me is Ceres, is to get a sample back from Ceres. And we know a lot about Ceres from the Dawn mission. And that's a really interesting, it's a dwarf planet now rather than the big asteroid. But that's probably it is a very water-rich world. And it likely formed, it's in the main belt now, but it likely formed much further out beyond Jupiter and Saturn. So it'd be interesting to know what the composition of that is. And actually, I'd quite like to know what the minerals are in there as well.
I'd agree with everything Ashley just said, and then add, like, going back to the graph, and there's nothing on the other side of the graph. Everything we're sampling is kind of out from our solar system. Love to get a piece of Venus. I know that's going to be really hard, or a piece of Mercury. That's gravitationally very difficult, I'm led to understand, but a piece of those objects to see what the kind of inward side of our solar system looks like. We don't have meteorites as far as we know from those two bodies. That'd be amazing.
Yeah. So we have Martian meteorites, and from those we have. You probably know better than me, Luke. We have some understanding of what the composition of the water is on Mars, in the same way that we know the Earth. But for Venus, we don't know anything, because Venus lost all its water. So we don't really know how much water is in Venus these days, and we don't really know what is it very similar to the Earth and Mars, or is it completely different? And Mercury would be amazing. It's not impossible. It's not impossible.
Lava field.
Yeah.
That's a topic for another day, but a very exciting one. All right, I'm going to take some audience questions now. Thank you both for answering all of mine. Let's see what we've got here. Okay, we've talked a bit. I think I have these two sort of questions that kind of go together. We've all talked about how Earth has gained its water, but is Earth losing water to the atmosphere, outside the atmosphere as well? And if so, how fast? And sort of in conjunction with that, why doesn't Mars have water? Because I think those two things are sort of related in the mechanism.
All yours, Luke.
All mine? Okay, yeah, cool. I'll go for this. So Earth is losing a little bit of water from just to space. But it's not necessarily that much of a problem, because we're protected by our beautiful magnetosphere. So those like high energy particles, if that turned off, some of our atmosphere would quite rapidly get stripped by solar flares, solar wind, etc. So part of the process that give us water in the first place might actually cause us to lose it. Some water goes down subduction zones into the Earth and gets recycled. Some water comes back up again at mid-ocean ridges. So we kind of replenish and recycle our water quite effectively. And some, indeed, does come down on us. What's interesting, for the deuterium-hydrogen ratio, it might slowly increase the D value over time as we're losing the kind of lighter isotopes of hydrogen to space and keeping the heavier ones. So that might be something we need to consider going forward. Basically, we do lose a little bit of water to space, like we lose a little bit of mass every year, but not appreciable over geological time. Mars, kind of similar reasons as you kind of alluded to, lost a lot of its water because its magnetic field switched off very early, lost its magnetosphere that was protecting it from the sun, solar wind, and galactic cosmic rays. That effectively blew off its atmosphere very fast. Then as soon as you put water in essentially a very low pressure environment, it sublimes, bubbles off, turns into a vapor, and then eventually it gets lost off the top of the atmosphere. And the other problem is Mars is substantially smaller, so much less gravitational field, so isn't able to effectively hold on to its atmosphere. So that's why Mars's atmosphere is relatively thin, and whereas Earth, much more massive, has that magnetosphere, is able to effectively hold on to its atmosphere much more strongly. Anything to add?
No. Yeah, no.
And that actually answered another question, which was, did the Earth's magnetic field play a role in our retention of water?
It's almost one of the most important points.
Yeah, crucial. Don't turn it off.
Yeah.
So do we think that there is enough water in our asteroids to mine that water in case we needed it for something, or to use it for missions or anything like that?
Yes. There's and so in those water-rich asteroids, there's more than enough water for you to do that. And some of Luke's work has shown that even in those asteroids that we think are probably very dry, there probably is a significant fraction of water trapped from the solar wind and things. So absolutely yes. What I would say there is that the challenge is, I mean, most of our asteroids are very small and they don't have any gravity and they spin very, very fast. So if you imagine, for OSIRIS-REx, they had a good idea. They went to asteroid Bennu and they had a pretty good idea that it was going to be a sort of spinning top type shape, and they knew it was very dark. But until they got there, they didn't really know exactly what the surface of that asteroid was going to look like. And they sort of planned because they were thinking the surface was going to be very fine grained, and it turned out it's covered in great big boulders. And so we don't really know anything about asteroids. So we haven't visited very many. And so the idea of, I'm not saying it's never going to happen, but the idea of landing and mining anything is a long way down the road, I think.
Yeah.
I
was
was
a little caveat, and it's not like I said, mining asteroids as a whole might be a way down the track, but NASA's plans for the Artemis program to put people back on the moon in a permanent fashion will need us to find water at the lunar surface for oxygen, fuel, water for the astronauts to drink. And the solar wind might help with that because it should be bombarding that surface of the moon. We're currently doing experiments to see if we see the same thing we saw on Itokawa at the lunar surface. And what's nice is it could be a relatively easy renewable resource of water as you're constantly streaming hydrogen ions in on the dust on the lunar surface. And we can get it out relatively simply because another process of space weathering is it makes iron nanoparticles in the outer surface. And there was an amazing experiment done in like the 60s or 70s because someone got permission to put lunar soil in a microwave. And if you know anything about microwaves and metal, those two things don't go together. It resulted in all the lunar soil melting and exsolving the helium and the hydrogen and the water from the solar wind. So put a microwave on the Artemis program and you can get water out of the rocks.
That's a new one for me. I like that. I have to admit, I did work on the citizen science that was mapping Bennu to do the tag sample.
Okay, yeah.
And we are very scarred from all of the boulders and rocks because it was sent to us with the expectation that we'll find some nice smooth areas for them to do this sample return, and then that did not happen. So yeah, we don't know as much about asteroids as we thought we did.
There's just no gravity. So these things, Hybris 2 and the one that went to Ryugu and OSIRIS-REx, they literally kiss the surface and then back away. There's nothing to keep them there. So Hybris 2 actually had a couple of little robots that went down, basically two small boxes on some springs that sort of hopped around for a little bit and took some images. But landing anything bigger than that on these things and then trying to put, or a microwave would be very difficult, I think. But yeah, there are lots of clever people out there who are trying to do this. So when we
and Bennu didn't even kiss it. It actually went in about half a meter.
It kept going, yeah.
So it was like, no, back off.
Yeah,
now we can't get the door closed. We have too much. Yeah. So.
Yeah.
So someone is asking, and I think this is a really good question, sort of relating back to these inner solar system planets. How would hydrated rocks survive the surface temperature on Venus? Would they be able to?
No. Yeah, I mean, that's part of the reason that Venus doesn't really have any water today. It got very, very hot and it lost all that water. So there may be water still in the mantle of Venus, possibly. But we don't know. I mean, Venus maybe is active now. We don't know. But no, it was too hot. It was too hot and just gone. And I think it was, I can't remember which mission it was that measured. You could actually see the stream of hydrogen particles being stripped off the surface. It was an ESA mission. Can you remember the name of it, Luke?
No.
There's not been very many Venus missions. I should be able to remember that. But they could actually measure that. They could actually measure the rate of the water coming off of Venus. So,
yikes. Okay. Has anyone compared the water ices found on Mars using the rover's instruments to what we have here on Earth? Has any of that been compared yet?
So not to my, no, I don't think so. And part of the challenge is that we do these measurements in the lab through a technique called mass spectrometry. We basically take the sample and we split the hydrogen deuterium and we count. And some of these instruments, Luke can do something atom by atom, but that machine is probably much bigger than an atom. And some of these mass specs can be very big. Some of them fill whole rooms. And actually, I've been at the synchrotron for the last few days, which is a huge facility for doing these, analyzing these things. So the challenge with rovers is that you just can't build all the experiments and the kind of equipment you need to go on a rover to do the same experiments. And it's part of the reason we need sample return, is because we're kind of limited to what the rover can do. And so if you bring the sample back, we can do so much more of that. So I'm not aware of anybody doing isotopic measurements on Mars. And they're certainly doing chemistry of rocks. They're certainly of the rocks, but I don't think anyone's looking at isotopes yet. I think we'll wait for samples.
I think the majority, again, I think you're right. I can't think of anything off the top of my head, but I think the majority of our understanding of isotopes, particularly of water, come from Martian meteorites.
Yeah.
So we measure water-rich minerals like apatite, clays, etc., in Martian meteorites to get an idea about what the deuterium-hydrogen ratio of Mars should be.
Yeah.
Okay.
But they did build for the Rosetta mission to go to Comet 67P. They did build a very, very mini mass spec to go on the Philae lander that landed on the surface, and so they did lots of isotope work for comets. But so it is possible.
Again, showing that it's very difficult to land on small rocky bodies.
Yeah, didn't quite go according to plan.
I think I've got like one last question here. They're asking if interstellar space is full of sort of hydroxide ions, how could these be combined to make a source of water and oxygen?
So in interstellar space, so if you've got hydrogen and oxygen, they would like to bond together. So you can do it. You obviously need the right temperatures and pressures. That's your kind of limiting factor as to what state that will be in. But certainly, I think in interstellar space, it's possible, or maybe even likely, that you have dust grains that have kind of icy mantles around them. And we see some it's one of the things I'm really interested in, actually, but we see some sort of tentative evidence of this on grains that we can see in certain types of meteorites. But these are tiny, these are micron sized. So if you imagine human hair is about 50 to 100 microns in size, these are much, much smaller. So there's some hints at that. So, but yeah, if there's hydrogen and oxygen knocking around, they will go together under the right conditions.
Luke, anything to add to that?
Yeah, no, I agree. Yeah, the wrinkle in interstellar space is the pressure is so low. So getting a isolated hydrogen atom and an isolated oxygen atom to marry up and get together and produce a water molecule it will happen because the universe is a big place, but it's an unlikely interaction.
Yeah. And you also have, the very radiation-rich environments and galactic cosmic rays and stuff. They can do a very effective job of breaking that bond as well. So you often have two competing processes going on.
All right, that's pretty much all of our audience questions. So thank you very much. I have one last question for each of you. When it comes to this whole solution, and it seems to be one of these, every time you figure out a piece of the puzzle gets a little bit bigger and a little bit finer. So it's no longer just like, here's water, here's how it gets here. It's now like, okay, well, now we need to measure these numbers, and oh, that number doesn't match, so now I have to look at this. So as your puzzle is getting more and more detailed and you're needing more and more pieces to it, how would you still say that it is easy for a body to acquire water in the universe?
Yes, it looks like it. I mean, we have evidence. The Earth clearly has water. Mars has water. Venus has water. Mercury probably had some water. So getting some water, I think, is easy. Water. We see water all the way through the solar system. Holding on to that water, as Luke mentioned earlier, that's the challenge. I think is where does that water go, and that really is related to the size of that planet, the location of that planet within its protoplanetary disk, its kind of geological evolution. And water plays a really important role in the geological evolution of planets as well. So it's not just a simple water. So, but yes, yeah. And then if you've got things like solar wind, adding even more water in there as well.
Yeah. I'm going to say, like, as soon as you get beyond the snow line, so much water, more water than you can ever do. That's why we've got stuff like Enceladus, Europa, which are basically these water worlds with these subsurface oceans. Even further out, you've got like potential oceans on Triton and Titan, etc. So beyond, like, so in the inner solar system where it's nominally supposed to be dry, we're seeming to have water everywhere. And that's even more exacerbated in the outer solar system. So kind of going back to like looking for life elsewhere in our universe, and we've been following the water for so long. Water seems to be common. It's not the be all and end all of a planet's ability to start to have life emerge on it.
But it makes sense. Hydrogen and oxygen are two of the most abundant things out there, and they like to bond together. So it makes sense there's lots of water available for planetary bodies.
So basically, water is not the limiting factor because it's just everywhere.
Yeah.
Yep.
All right, great. Thank you. Frank, you're
unmuted. Yes, I know. I had to do it once at least today. All right, thank you. That was a very interesting conversation. Thank you very much, Luke and Ashley, for enlightening us about water and the original water. And this is going to be an interesting SETI talks. And I'm glad we are going to have a recording of that on YouTube and other platforms. So people who want to hear it again or want to have the opportunity to take the time to think about where the water comes from can just watch that soon on our other platform. Thank you very much, Beth, for moderating this conversation. You were amazing, admirable as usual. And no doubt that it will be a great talk, and you asked the great questions. Thank you to our audience as well. We are almost 200 people watching us live today. I'm going to say a few places just so you know that we have people in the US, from New Jersey, Denver, Crystal and Richfield in Minnesota, San Francisco, Fort Bragg, Point Reyes in California, Chicago, Carson City in Nevada, Austin, Texas. Hello, I was there last week. And of course, people from Louisiana, in Lafayette, Hawaii as well. In Europe, we have people from Glasgow, London, maybe a few colleagues, Bristol, Reigate. I have no idea where is this, and I will look on the map. Elsewhere in Europe, Paris, Barcelona, Düsseldorf, Bulgaria, and around the world in Haiti, Australia, Montreal, Quebec, Toronto, India, Goma in Congo, Chiba in Japan. So this was a SETI talk, and we talk about the original water. This is a talk organized by the SETI Institute. We are a non-profit organization. You can visit our website at seti.org. If you feel inclined, you want to support this kind of program, you can make a donation. Go to seti.org/give now, and you can make a small donation to support this program that is monthly. And we try to invite a diverse group of researchers to talk about everything happening in the field of astrobiology, trying to bring to use some of the most recent results in this area. Today we talk about papers which has been published, research which has been published over the past 5 years. So that's quite new. And I really appreciate, Ashley, Luke, you took the time to join us and to talk to us about your work and your research as well. Next month, we are going to have a SETI talk, which is going to be a bit special because it's going to be hybrid. It's going to be in person at the SETI Institute headquarters in Mountain View, California, and also on Zoom. I will be on April 19. The title is not yet finalized, but it will be something like, "Are they watching us?" Talking about whether or not technological alien civilization can detect us from far away and how they will be able to detect us. So that's going to be a very interesting talk if you are interested in SETI, but we will talk also about astrobiology in general. So that's all for this month. You can go back to your real activity, back to your real life. Enjoy the water that you can drink, because every time you drink, think about it, you're drinking maybe a piece of an asteroid or comet, or maybe a piece of some ions coming from the solar wind. So thank you again. Thanks, Ashley, Beth, Luke, and see you maybe in person in the future at the conference. Bye-bye.
Cheers. Bye, everyone.
Thanks very much.
Bye, everyone.
Bye.
Thank you.